Hi, welcome to this talk on the patterns and practices for building resilient serverless applications. But first, let me define what I mean when I say resilience. The dictionary definition of resilience is the capability to recover quickly from difficulties or toughness. In other words, it's not about preventing failures, but to recover from failures quickly, because as Amazon CTO Werner Vogel famously said, everything fails all the time. It's a fact of life, and there's nothing we can do about that. But what we can do is to build applications that can withstand different forms of failures and be able to recover from them quickly. For example, in a data center, hardware fails all the time. And to withstand hardware failures, we run our applications on multiple servers so we can withstand failures to individual servers. And since data centers, or in AWS terms, availability zones can go down in exceptional circumstances, of course, it's not an everyday occurrence. But we still run our applications across multiple availability zones, or maybe sometimes even across multiple regions, so that when these unlikely events happen that affect entire availability zones or even regions, our applications can continue to function as normal. And since individual servers have a limited set of resources in terms of CPU, memory, and bandwidth, the more users' requests a server has to handle concurrently, the more resources that we have to use. And a common failure mode is that when there are too many concurrent requests and we saturate the CPU, after which point latencies start to spiral out of control. It's another reason why we need to scale out our application across multiple servers. And when we have a distributed environment where services often have to coordinate with and depend on other services, and sometimes when one service experiences some kind of failure, they can often cascade throughout the entire system and affect even those user-facing services, which of course is not going to make your customers happy, because all they want to do is to use your app, and suddenly they can't, and they have to experience some kind of interruption when those cascade failures happen in the system. And when you have a microservices environment with lots and lots of microservices, is quite a common problem that many of us have to deal with. And my name is Retry. I'm an AWS Service hero and a really long time user of AWS. I've been running production workloads in AWS for more than 10 years at this point. And in the last couple of years, I have focused primarily on the serverless technologies, including migrating a social network to run basically entirely on serverless a couple of years ago, which you can read about on this link here. So nowadays, I spend half my time working with Lumigo as a developer advocate, and Lumigo is a troubleshooting platform for serverless applications, and it gives you a single place to see all of your distributed traces, logs, as well as the state of your Lambda functions during an invocation, and really help you debug problems quickly. The other half of my time, I work as an independent consultant, and I help companies all around the world go faster for less by adopting serverless technologies. So back to the talk. So this diagram from Uwe Fredriksson, which I'm pretty sure I butchered his name, highlights the four broad areas that we should consider when we think about resilience. And it's worth considering that AWS Lambda gives a lot of resilience out of the box, not least because we have an isolated execution environment for each and every invocation. So if one user request uses up too much memory or CPU, it has no effect on any other user requests. And when you build applications and APIs with API Gateway and Lambda, you get multi-AZ out of the box, as both API Gateway and Lambda deploys your resources to at least 3 availability zones by default. And both API Gateway and Lambda, they both charge based on usage, so you only pay when users actually use your system. And what's more, you also get load balancing out of the box as well. When an HTTP request comes into API gateway, it's routed to one of the availability zones. And again, you don't have to configure and pay for those load balancers yourself. You just get it. And finally, if you're using DynamoDB as your database, then you also get the multi-Z by default for your database layer as well. And you can also configure DynamoDB tables as global tables and basically turn your entire API into a multi-region active setup, which is basically the gold standard for building resilient APIs on AWS, but more on that later. So it suffices to say that we get a lot of resilience out of the box with serverless technologies like API Gateway and Lambda and DynamoDB, but we also have to be careful in terms of the built-in throttling at each of these services, especially as they don't always align perfectly. This also applies to timeouts as well, whereas API Gateway has a maximum integration timeout of 29 seconds, which is a hard limit, even though Lambda functions can run for up to 15 minutes for a single invocation. And the same also goes to when you process Sqs messages with Lambda, where you have to consider the visibility timeout on the queue and how it relates to the Lambda function timeouts you have. The general recommendation is that the Sqs visibility timeout should be 6 times the Lambda function timeout. So make sure that you give your functions enough time to process the messages before they become available for processing again. A very common pattern for making your APIs more resilient, at least in cases where we need to do CPU intensive work, is to offload the task to a queue first so that the API function can respond to the caller quickly. And then we can do those long-running CPU intensive tasks in another Lambda function where we don't have to worry about API Gateway's 29-second timeout. So this allows us to better absorb any sort of downstream problems. For example, if we need to call some third-party API, and if that API's latency goes up, we don't run the risk of getting timed out by API Gateway after 29 seconds. And we also get the retries through Sqs as well, and even when retries don't work, there's also the DLQ support as well for poison messages. But a common problem with DLQs is that we need some way to replay those DLQ events, especially if the original failures were down to temporary issues with, say, some third-party services, or potentially some connectivity issue or credential issues with our configuration for our application. So that once those problems are solved, then those messages can be replayed and reprocessed safely. To do that, you can use the Lumigo CLI, which contains a bunch of helpful commands, such as the replay Sqs DLQ command that lets you replay messages from Sqs delta queue back to some other main queue, or if you want to forward messages to a SNS topic instead, or Kinesis stream, you can do that using the same command. So this pattern of offloading tasks to some background queue and then process them out of hand is great for fire and forget task, where the caller doesn't do anything with the response, and it just needs some kind of acknowledgement that the task has been received and be processed in the background potentially. But what about cases where the client does need a response from the API, and because it needs to do something with those responses later? A really common, well, maybe not common, but at least the related pattern is called the decoupled invocation, where the main difference to what we just discussed is that it will return a location header in the initial response so that the caller can then poll for the result until it's ready. So in this case, a request would come in, and our API function is going to queue up the task in, say, Sqs, and then it's going to save a token in a DynamoDB table where result is null, as in it's not ready yet. It will return a 202 response to the caller with a location header, And in the meantime, SQS function is going to pick up the task and then start working on the task. This, remember, could be some CPU intensive and long running job that can take maybe a minute, 2 minutes, or maybe even more. And when the client polls for the result in the meantime and it's not ready yet, our API can then just keep returning 202 and keep saying, sorry, it's not ready yet, but here's a location header for where the response will be once it's ready. So the client can keep polling every, say, a couple of seconds or whatnot. But when the background worker finally finishes the task and then it saves the result into the DynamoDB table, then the next time the client asks for it and polls for the result based on the location header, we can then finally see the result in the database, and then we can return it and return a 200 response to the caller along with the result. So it's fairly straightforward, right? But wait a minute. Notice that we have a distributed transaction here, where the API function has to write to both SQS queue as well as writing to a DynamoDB table in the same invocation. Which means if we are to do this the right way and do this properly, then we need to make sure that if one of these operations fails, then we have to roll back the other. We don't want to say keep the message in the queue if we couldn't write the token result into the DynamoDB table, so that when the caller polls for the result, we don't have anything to respond to them with. So we need to have some kind of rollback in place. So how should we implement this kind of distributed transactions properly in that case? Well, there's the Saga pattern, which is the pattern for managing failures in a transaction, where each action in the transaction has equal and opposite compensating action for performing the rollback. There's this talk by Katie McCaffrey from, I think that was 2015 maybe, which she gave really good examples about the Saga pattern and if you want to learn more about the Saga pattern, then please go and check out that talk. So basically, you may imagine you're implementing some kind of a transaction for a holiday app where you need to book a hotel and then a flight and then a car rental. Each of these actions, as well as their rollback actions, can be modeled as Lambda functions. And we can use step functions to coordinate the Saga, and step functions is another service that AWS provides, which allows you to model business workflows and other things as a state machine, and then you're able to execute the state machine with some input. And in this case, we can model our distributed transaction as a Saga with multiple steps using step functions and model that Saga as a state machine. So that given an input like this one, where I'm visiting Dublin from London, the happy path is going to have me book the hotel and then the flight and then the rental, and then it's going to complete the transaction successfully. But if there was any failures, then we will perform the rollback action to undo any state changes that we've thus been done in the system so far. And if we had booked the hotel, but we couldn't book the flight, maybe the flight is fully booked or the prices have changed, then we need to roll back both the flight as well as the hotel booking steps as well in reverse order. So we'll first cancel the flight, and then once that's complete, then we then also have to cancel the hotel booking as well. And you may also notice that there's some like a self-recursion here. That's if we say the cancel step failed, then we want to have some kind of a retry to make sure that we give it a good few attempts before we give up. So the Saga pattern is a really powerful pattern, and it's really useful as well, especially when you have more complex transactions. But it's also just extra stuff that we have to do. For many of the simpler cases, we can actually architect the distributed transaction out of the application by using DynamoDB streams instead, where a Lambda function would write the task into a DynamoDB table, and then we rely on DynamoDB streams to trigger another Lambda function who would then take that event, the new data that's been inserted into DynamoDB, and then it would transform it into some kind of business event, and then it will queue the task into SQS so we don't have to have any kind of distributed transaction in that initial API function. And in this case, there's no distributed transactions in the system because we're delegating the second step of our transaction to DynamoDB streams, triggering a second Lambda function. Or we can even do even better. We can just do the work in the DynamoDB function, where the DynamoDB stream is already a queue of sorts. So unless we're getting something extra with Sqs, we don't have to use it. And with DynamoDB and the Kinesis streams, there's also this really interesting error handling behavior where messages are retried until success, which can be very useful in situations where the only thing that's likely to go wrong is when some third-party system is having an outage. Then, since the messages are retried until success, there's nothing really for us to do. When the third-party system is back online, we will just continue from where we left off before the outage, and the system will just keep on working at the maximum throughput allowed based on the number of shards we have in the stream, and it's just automatic. There's nothing for us to do, which is awesome. But the thing to keep in mind here is that DynamoDB streams only keeps data for 24 hours, and there's no way for you to extend that. So if it's possible for an outage to last for more than 24 hours, then we need to have alerting in place so that we can deal with any issues quickly before any data loss happens. One thing we could do is to turn on the on-failure destination. Essentially, this is the delta Q for stream processing Lambda functions. Another thing that we to keep in mind in this setup is that the retry until success behavior can also render us vulnerable to poison messages, because if there's a message or event that we couldn't process for whatever reason, it's going to stop us from being able to process subsequent events that's been published into the stream potentially. So what we could do nowadays is that we can configure the max number of retries and also have the option to split a batch when it couldn't be processed, so that we can quickly home in onto the poison message. So in this case, with Kinesis and DynamoDB streams, both are batched event sources for Lambda, so you typically process batches of events as opposed to one event at a time. So what you could do is to say, if batch had, say, 6 records, after the first attempt, our function couldn't process it and it threw an error. The second time Kinesis fires the event to our Lambda function, the batch will be split in half so that the second attempt will only process the first 3 records, or the first half of that initial batch. And if that still fails for whatever reason, then it's going to try it again later, but this time it's going to split the batch again, and so you're just going to get 1 record. And so from here, if that 1 record it still fails, it will be retried up to the maximum number of retry attempts that you've configured above. So here you have to keep in mind that this sort of retry attempts only counts the number of attempts of the same batch. So in our example, you start counting when we're down to 1 record in the batch. So in total, the poison message would be attempted a few more times than the maximum attempt value here, because of the fact that the batch was split multiple times before you get down to that 1 record that is the poison message. You should use these 2 options together to avoid otherwise normal messages from being discarded because of a single poison message in a batch, so that once you process that poison message a few times, it couldn't be processed, and it's going to get sent to the on failure destination, which could be a Sqs queue where you have some alert set up so that when those messages are put into the queue, you find out about them quickly. And when those poison messages is eventually discarded, it's going to end up in your on failure destination, which typically is your delta queue. The message is going to look like this. The key thing to note here is that you don't have the message body. So you have to use the shard ID and the sequence number to fetch the actual message itself from the stream. And don't forget, you got to do this before the data actually expires from the stream. So again, you need some kind of alerting in place so that you do this proactively or have some other process to automatically read the data from the stream when poison message is forwarded onto the delta queue, so that you read it straight away from the DynamoDB stream or the Kinesis stream, and then you save the the message body somewhere else. And as for using Sqs and Lambda functions, since Sqs is a poll-based service, there's actually a cluster of pollers that Amazon operates on your behalf, polling from the queue and then forwarding batches of messages to your Sqs function. And when our function finishes with no error, the poller is going to call Sqs to delete the message. And the problem comes when our function actually threw an error. And so the poller doesn't call Sqs to delete the message, even though, again, Sqs is a batch event source for Lambda. So even when our function couldn't process a batch, chances are it may have been able to process some of the messages successfully, but not others. So those messages would eventually become available again after the visibility timeout, and then it's going to get retried. And after the maximum number of retries, hopefully only the poison messages would continue to fail after those retries. So as they are then picked up again by other Lambda functions, maybe in different batch configurations. So after multiple retries, multiple failures, only those poison messages are then delivered to the delta queue. Again, if you're using Sqs with Lambda, you should definitely and should always have delta queue when you process those messages with Lambda. But the fact that the batch fails as a whole means that we have to deal with those partial failures. And I've discussed this along with a few other Sqs failure modes to consider in the blog post a while back. Ultimately, I think you have three main options here. One is to just use the batch size of 1, which kind of eliminates the problem altogether, but it can hurt your throughput, and it can also add to your cost as well, since you need to have more Lambda invocations and more API requests to Sqs to process the same number of messages. So generally speaking, you do want to process messages in a batch for efficiency. Or second option is you can make sure that your processing logic is idempotent, which I think you should always aim for anyway, but it's often difficult to actually achieve in practice, especially when you need to update the state of multiple systems, which would necessitate more complex mechanisms like using a saga pattern to make those distributed transactions safe. Which is why my personal preference is to just put a try-catch block around each message when you process them with inside your Lambda function. And if everything is processed successfully, then you just return from your function as normal and allow the poller to then delete the messages as it normally does. But if there's any failures, your try-catch will hopefully catch those specific failures, those messages that couldn't be processed. And then what you could do is your function can then call Sqs and call delete message on the successfully processed messages, and then just throw an error. Let the error bubble up, and so the poller sees, oh, your function couldn't process this batch. I'm not going to call delete message on those messages I send you, and later on the messages that couldn't be processed will be picked up again after the visibility timeout has expired. Here you have to be sure to call delete message on the successful messages yourself in the event that some of the messages couldn't be processed. So it adds a bit of complexity, but otherwise it allows you to handle those partial failures more gracefully without resorting to more, I guess, extreme measures of like using a 1 as your batch size, or having to put into place in place more complex mechanisms like a saga pattern. And moving on to another common problem in microservices, where sometimes doing the right thing can actually have the opposite effect. So imagine we have Lambda functions that need to call this service A, and at any moment in time we have a number of concurrent executions. They're all calling the same service. Now imagine that this service is having some kind of problem. Some of those requests are going to fail or maybe timeout, And to make our application more resilient to temporary issues like this, we probably have some retries with exponential backoff built into the application. And in the normal situations, this is absolutely the right thing to do. And the Amazon SDK do this by default for all the services, by the way. Except in some cases, in the maybe in this particular case, the service A is already struggling. It has to deal with the retries as well as fresh requests from new concurrent new requests from other invocations. And since it's struggling, it can't handle all of these requests. And so the failed request is going to get retried again, and so on until the service is just dead on its feet because it just never get a chance to recover. And this is what we call a retry storm, where problems can sometimes be exasperated by doing the right thing and retrying failed requests. And the solution is to use a circuit breaker pattern where you still have retries, but after a number of consecutive errors or timeouts, you trip the circuit so that no more requests can be made to this service, and any requests would just fail outright. We just throw an error, maybe like a circuit is open exception or something, and we're not even going to make the request to the service because we know it's struggling, and we're going to give it a chance to actually recover. So instead, we're going to let just one request through every, say, couple of minutes to see if the service has recovered. And if that request was successful, then we just assume that things are back to normal and we will close the circuit. Otherwise, if the request still failed, then we're going to keep the circuit open and we're not going to let any requests through for another few minutes. And then we're going to let another one request through just to see if it has come back to life. So this is pretty common practice in microservices. The big question for a serverless application is, where do you put the state of the circuit, since concurrent executions, they don't share state. They're all executing in separate environments, which is one of the things we talked about before, where it's a benefit because if one user request uses up too much resource, it's not going to affect any other user requests. So the two ways I think you can do this, you can either let each concurrent executions track its own state, which is simpler and have no external dependency, but it does in this case allow more requests through before it even identifies that, okay, this service is having a problem and we shouldn't make any more requests to this service. Or potentially we can store the state of a circuit in some external service to our function, say a DynamoDB table. In this case, we can minimize the total number of requests to the service before we trip the circuit, and say when a new concurrent execution comes alive, and it can just check the DynamoDB table to see if this circuit is open. And if it is, then it doesn't have to, it knows the circuit is open straight away. It doesn't have to let a few requests through before it even realizes that this service is not working well. The downside for this approach is that it does add a little bit more complexity, and it also adds another dependency on another service, in this case the DynamoDB table, which you may argue that is another thing that you have to protect using a circuit breaker pattern. So personally, I would like to start with the in-memory approach first, and then if it doesn't work because it's just letting too many requests through, and we are seeing the time to discovery of a problem is too long, then okay, we will change our approach and upgrade to using DynamoDB tables, if and only if it's the simple approach is just not good enough, and we do need to reduce the number of requests that gets through during an outage. And then finally, there's the gold standard for building resilient serverless applications, which is to make them multi-region active-active. Imagine you have a REST API with API Gateway, Lambda, and DynamoDB, all running in US East 1, and all sitting behind a Route 53 record, and with a user-friendly domain name like api.myapp.com. Now, this setup is already pretty resilient, as all the components have redundancy across multiple availability zones, but you're still vulnerable to region-wide failures, which doesn't happen often, but when they do happen, they can knock out all of your services that are running in that region. So to get to the next level of resilience, let's go multi-region instead. By deploying our application to 3 separate regions and to serve requests from all 3 regions all the time in an active setup using Route 53 to route traffic to different regions, probably using geolocation or latency-based routing so that the user request is always routed to the closest or the region that has the lowest latency for this particular user. And to make sure that all the data updates are synchronized globally, and by connecting the regional DynamoDB tables together as a global table, and basically let Amazon manage and synchronize the data for us. And then we need to set up a Route 53 health check so that if one of the regions goes down for whatever reason, then the traffic can be routed and diverted automatically to the remaining regions. And of course, this is subject to the TTL that you have configured on the DNS record set. And this approach is not limited to APIs as well. You can also apply this to your data processing pipeline. For example, suppose you have a pipeline that ingests data from an upstream SNS topics through Sqs and Lambda, and the data is written into some DynamoDB table, which is then used to actually power your API with API Gateway and Lambda. And suppose your upstream system is already running multi-region active, then you can subscribe your queue to both the SNS topics in both regions and ingest data from both places, so that in the event that one of the regions goes down for the upstream system, then the pipeline will still continue to work without you having to do any manual intervention. Amazon engineers call this static availability, where the system will just continue to operate in the face of availability zone or regional outages. However, in this setup, you end up ingesting the same data twice, so you do need to do some kind of deduplication somewhere. It can be done using conditional writes when you insert the ingested data into DynamoDB, and to make our data pipeline and API multi-region active, we would deploy the same setup to 2 or more regions, and then set up global table for all the regional DynamoDB tables again. And so here, each region will subscribe its SQS queue to both upstream SNS topics. So that once again, if one of the upstream regions go down, the system will just continue to operate without any manual intervention. And of course, we will have Route 53 in front of our API gateway, so that in the unfortunate event that the whole region goes down, then our system will still continue to operate. And it's going to self-heal once the TTL on the DNS records expires and API traffic is then diverted to the healthy region, all without requiring you to do any manual intervention. One of the great things about doing this with serverless components is that there's actually very little overhead for having the actual redundancy compared to running containers or VMs, where the diluted traffic to each region and the availability zone means that you end up spending a lot of money for unused resources, because you still need that headroom in each region in case the other region goes down, and then all the traffic is then suddenly diverted to one region. And the downside of having a multi-region setup like this is that they are just more complex. Everything from deployment to monitoring just gets a bit harder, and they're also more difficult to test as well. And speaking of testing, the best way we have for testing some of these more complex systems is chaos engineering, which many of you hopefully would have heard about from the likes of Netflix or Amazon, talking about how they would kill their servers in production at random to simulate infrastructure failures that results in the loss of virtual machines, and see if the system can still stay up when those infrastructure problems happen. It's certainly one way you can apply the principles of chaos engineering in practice, but chaos engineering itself is much broader, and in the words of principlesofchaos.org, which is one of the best places to go and read if you want to get started with chaos engineering and understanding its core principles. It defines chaos engineering as a discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And it's becoming increasingly important to many organizations because we are just building more complex systems now, which have more complex and hard to predict failure modes. And the thing about failure is that, be it hardware failures or software bugs, you just don't choose when they happen. The moment chooses you, and you can only choose how prepared you want to be when it does happen. And the great thing about chaos engineering is that it's not limited to just your application. It can be applied to test your infrastructure and the platform, as well as the people and processes you have in your organization as well, through things like game days. And in terms of tooling, you probably heard about Netflix's Simian Army, where you have a bunch of different monkeys for killing servers or injecting latency or killing an entire availability zone or even a whole region. This, however, are not so useful when it comes to serverless, since we don't have access to the servers that runs our code, so there's no servers that we can actually queue as part of an experiment. And AWS is already doing all sorts of experiments to make sure that the Lambda service itself and the infrastructure beneath it are highly resilient, so as a customer, I don't have to worry about individual servers dying and the hardware failures. But I'm still responsible for my application code, and I can still use chaos experiments to identify weaknesses in my application. And even though by using serverless technologies like Lambda and API Gateway and DynamDB, we are getting a lot of built-in redundancy and resilience, as you've seen in this talk, there are still lots of ways applications can fail. And sometimes simple mistakes like having a mismatched timeout values can mean that your user-facing APIs can time out while waiting for response from your internal services if one of its dependencies is having like a slow day in the office. Or maybe I'm just missing some error handling, which is incredibly basic mistake to make, but also incredibly common in practice as well. And in cases where, say, a downstream system is having an outage, maybe I'm missing a trick by not having some kind of a fallback strategy so that I can return some cached or maybe even a default response so that I can mitigate a cascade failure here and allow the system to fail more gracefully. Luckily, I can use tools like Failure Lambda to inject failures into a Lambda function and run experiments to see how my application behaves when those failures happen. For example, I can use it to inject failures into Lambda functions whenever it tries to connect to DynamDB to see how it behaves if DynamDB has an elevated error rate. Or what's going to happen if a service that my function depends on has an elevated latency, by injecting latency to the HTTP requests from the Lambda function to that service to see what happens. I can tease out all kinds of failure modes proactively and identify weaknesses in my system before they actually happen in production, and they will eventually because everything fails all the time. But what we can do is to build applications that can withstand those failures and recover from them quickly. And that's everything I have. As I mentioned before, I work as a consultant, so if you need some help with serverless technologies in your organization, then feel free to check me out at theburningmonk.com. And I've also had a new video course on AppSync, which is available now. You can see how you can use service components like AppSync, Lambda, DynamDB, Cognito, and so on to build a pretty fully fledged Twitter clone. With that, thank you very much and stay safe.
Hey, it's Joe Eames with ng-conf. If you like that video, be sure to click subscribe either here or here, somewhere over here. And if you're looking for something more, here's another video for you to watch here or there or somewhere.